Welcome to another National Training Center TechByte. This one will cover medium and high voltage bushings, specifically directed at the insulation testing and evaluation associated with C1 and C2. TechBytes are usually quick videos that will be from 3 to 8 minutes in duration. Due to the complex nature of some topics, some of these videos will be up to 20 minutes in duration. They're designed to cover a very specific topic or issue associated with the world of electricity. This video is approximately 16 minutes long. This TechByte topic is associated with condenser type bushings. We will be covering only sufficient foundational information to get us to the C1 and C2 evaluation. Technicians and engineers must review and understand the test equipment they're using and the procedures required. The TechByte is insufficient to train a technician or engineer in power factor testing. It assumes the trainee has a foundational working knowledge and is specific to the evaluation of C1 and C2 tests. Additionally, this TechByte does not apply to spares or any other situation than bushings that are mounted and have been or are ready for service in the equipment. I'm going to go over a couple of bushing types here. Even though our primary focus is on condenser, we will at least look at what the non-condenser is. In simplified terms, the non-condenser is solid insulation like solid porcelain. There are variations of gas-filled, solid, and liquid layers, etc. But again, the focus of our discussion here is on the condenser bushing. The condenser bushing uses either oil-impregnated paper insulation interspersed with conducting layers. You will also find oil-impregnated paper insulation continuously wound with interlaced paper layers, and some condenser bushings use resin-bonded paper insulation with interspersed conducting layers. When we're using the term conducting layer or condenser, what we are simply describing is a capacitor. We will be referring to these terms singularly as capacitive layers for the rest of the training. The reason for this, what we are measuring is insulation, is quite simply capacitive nature of the insulation, which we do through capacitance. That is the reactive nature, watts, the resistive or heating nature, and the ratio of the two through power factor. A condenser bushing is a series of concentric capacitors between the center conductor and ground sleeve or mounting flange. A conducting layer near the ground sleeve may be tapped and brought out to the tap terminal. The tap bushing in many modern condenser bushings is known sometimes as the test tap. In some older designs at high voltages, this design affords a voltage divider network that is referred to as a potential or voltage tap and is sometimes used to provide secondary level voltages to relays and meters. First, we're going to energize the center conductor of the bushing. We will do this based on the voltage rating of the bushing itself. As indicated here, if it's rated over 8.7 kV, you should be using 10 kV. Rated between 5 and 8.7 kV, we're looking at 5 kV. Rated at 4.3 kV, we're looking at 2 kV. And finally, rated at 1.2 kV, we're looking at 1 kV for our applied voltage. We will actually be measuring the current through the layers to the bushing tap. Other currents to ground are not measured by the test equipment. This current should be highly capacitive. There are additional tests that can be done for C1 if the UST indicates a potential problem. Again, it's essential that you understand the manufacturer's instructions for both the bushings and the test equipment. This is simply an overview of the procedure. At this point, we need to make one point very clear. No engineer or technician should be executing tests on electrical apparatuses without understanding what is in the manufacturer's instructions, the standards and practices, and has an appropriate set of credentials and certifications. If you do not have education and specific training, there are many sources, including our training program, that can provide this. The power factor and capacitance should be compared to the nameplate of the bushing. Usually for C1, both power factor and capacitance are on the nameplate. If not, and in addition to, you really should compare it to prior tests and test on similar bushings. Modern condenser bushings should have a power factor around 0.5% after correction to 20 degrees C. Many bushing nameplates may be between 0.20 and 0.50% power factor. The capacitance should not exceed 10% of the nameplate for C1. Let me restate the manufacturer's instructions are essential. In the next slide, let's look at one manufacturer's take on acceptable results. Power/dissipation factor. As we're looking at the power dissipation factor, our XYZ bushing, which is just a generic term for our generic manufacturer, states that between 0 and 25% increase in power factor from previous results, the value is taken to the record and no further measures are to be taken. You'll notice, however, at 25 to 40% as we increase, the measuring circuit is checked regarding leakage and external interferences. The first thing they're doing here is they're checking to make sure their test setup is correct. External interference can, for instance, be influenced from nearby current carrying equipment and bus bars. If the difference remains, the gaskets of the oil level plugs are replaced because of moisture introduction according to product information for the bushing. The measured value is entered into the record and the bushing is again can be put into service. "40 to 75% increase measures as above, the measurement shall be repeated within 1 month." So what we're saying here is the manufacturer's telling us that if our values are above 40 to 75% increase from previous tests, we want to retest it in a month. Finally, if it's more than 75% increase, the bushing shall be taken out of service. However, if the dissipation factor is less than 4%, the bushing may be taken into service even with that 75 or greater increase from the low initial value. So what they're saying is, if you have a 75% increase over a previous power factor, then it should be taken out of service. However, if that 75% increase is still resulting in a power factor of less than 4%, then you can put the bushing back in service. It gets a little bit complicated sometimes, and that's why the manufacturer's information is so essential that we look at that. As to capacitance, the manufacturer does not want you to even run a C2 test. They state some of our customers do also want to use the capacitance C2 and dissipation factor over the tap insulation as a diagnostic tool. Based on our experience, we strongly recommend to avoid that. There are several reasons to not use those values as diagnostic tools. We're going to look at those reasons when we get into the C2 section. As it pertains to C1, if an increase of more than 3%, which could indicate partial puncture compared to the factory measured value, or an extremely low value is measured, please contact the manufacturer. Again, what we've just covered in this slide and in this section is the manufacturer's take on how they evaluate power factor, C1, and an indication to what we're going to be seeing with C2. Now let's look at how we evaluate these test results if we've seen them and what they mean. What does it mean if the power factor goes up or down, or the capacitance goes up and down? An increased capacitance over previous tests or other similar units or the nameplate could indicate shorted condenser layers. A decreased capacitance in the same sense could indicate open circuits, discontinuities, floating ground sleeve, or even more important, test procedures or equipment issues. Increased power factors it will indicate contamination or insulation deterioration. If you have a negative power factor, which will rarely occur, with reduced capacitive charging current, you're going to need to get a hold of an engineer, and there's going to be some more research done into the bushing itself, and maybe even consulting the manufacturer. Short-circuit condenser layers are sections of bushings that result in increased capacitance and charging current. It's important to note that decreased capacitance could be the floating ground sleeve, where we talk about the floating ground sleeve or the test lead problem. When you get this type of situation, you really need to check all your connections. There's so many different things that can be wrong. You can have a bad lead, you can have a bad connection to the test tap. So you need to make sure you check your test connections in your equipment if you have a problem with decreased capacitance. Now let's take a look at the C2 test. The first thing you should notice, instead of an ungrounded specimen test, this test is a grounded specimen test, or GST. When we energize the test tap here, we have to be very careful. Potential tap can be energized to 2 kV, a power factor tap to 500 volts. This is very important though. Some manufacturers recommend lower values than 500, and some recommend not even using C2 as we saw previously. Under no circumstances, do not energize a power factor tap over 500 volts unless the manufacturer or a licensed engineer has authorized it. And the licensed engineer is going to simply check with the manufacturer and check with some standards to make sure that what you're about to do is acceptable. Most of the time, my experience has been you're going to find that you will not go over 500 volts. So what are we testing with C2? We're basically measuring the core insulation between the tapped layer and bushing ground sleeve, the tap insulator, a portion of the filler, and a portion of the weather shield near the flange. As you can see here, we're actually testing that very outer layer to ground for all practical purposes. So it's not a very large circuit, or it's not testing all the way through to the conductor. We're testing the outer layer to ground for all practical purposes. Our expected C2 results are going to be a little bit different than what you saw with C1. The power factor and capacitance, again, should be compared to the nameplate on the bushing. If it is available, what you're going to find is the C2 sometimes is less likely to be available than the C1. Again, if it's available, we compare to that. We also will compare to prior test and test on similar bushings. The results here are not as clear-cut as with C1. If you recall our example manufacturer, they were not a fan of C2. Since there's so much variation in construction and manufacturing of bushings, it's essential, especially with C2, to consult the manufacturer. A slide that follows, we're going to look at our example manufacturer's actual take on why they do not recommend C2. However, if you're running the C2 test, generically speaking, C2 power factors should be around 1% after correction of 20 degrees C. Generically speaking, the capacitance should not exceed 10% of the nameplate. These by no means are reasons to fail the bushing. More consultation with the manufacturer will be necessary if you see test results outside of these parameters. Here we are with XYZ manufacturer C2. Let's look at what he says about C2. The test tap is connected to the outer earth layer on the condenser body. The solid layer outside the earth layer contain an adhesive together with cellulose to make the condenser body more stable. This means that the contribution to the dissipation factor from that part differ from the pure cellulose in the main insulation. It also means that this part cannot be used for diagnostic purposes, as the adhesive effect the dissipation factor different on different bushings. So what the manufacturer is telling us here is, based on the construction of his bushing, the power factor for C2 cannot be used for diagnostics. Let's look at capacitance. During operation condition, the outer layer is earthed. Consequently, the insulation between the outer layer and the mounting flange are not subjected to an electrical field and do not thereby cause any dielectric heat loss. It is likely that if the bushing is placed in contaminated areas, contaminants on the outside of the test tap will affect the results. Also, moisture around the test tap do also affect the measurement. This is the manufacturer's reasons why he does not accept or recommend and strongly recommends to not use C2. As with C1, we have a decreased capacitance would indicate an open circuit, discontinuities, floating ground sleeve, test procedures, or equipment issues. And also, as with C1, their increased power factor, contamination, or insulation deterioration is the result of that. It's important to note, again, that decreased capacitance could be dealing with your test connection, and you must always retest and check your test connections. In conclusion, there are many other tests that we have not covered that can be used for further investigation and to assist analysis. Modern test equipment can provide a reliable, acceptable results. However, when this equipment indicates a problem, we must continue investigation and additional testing to determine accurately the condition of any electrical equipment. You cannot simply fail a bushing based on a C1 or C2 test without doing some additional testing and some additional investigation. This concludes our TechByte on medium and high voltage bushings, specifically dealing with the insulation testing and evaluation associated with C1 and C2. Have a great and safe day.